Find the area of a rectangle of maximum area that can be inscribed in a semicircle of radius 4. What that's asking you to do is to put a rectangle inside this semicircle with maximum area. So that'll look something like this. So here is a rectangle. What do we know about this rectangle? Well, we know that from the center to the corner on the curved part of the circle, semicircle, we know that distance is 4 because that is exactly the definition of a radius. So what we really need is we need to know the length and the height of this rectangle. Well, I don't know anything about the entire length of this rectangle, but I can say something about this bottom leg of the triangle, that is x. If that is the case, then this part of the rectangle is also x. So we know that the entire length of this rectangle will be 2x. And in order to find the area, I will also need the height of this rectangle. And I don't know the height looking right at it, but I can use the Pythagorean theorem because I have a right triangle. So using the Pythagorean theorem, the hypotenuse squared, that 4 squared is 16, minus 1 leg squared, the x squared. If you take the square root of that, that gives you the third leg. So using this, we can optimize the area of that rectangle as it is the length times the height. The area, the optimizing equation, is already in terms of one variable. So we can go ahead and take the derivative of this. A prime is, by product rule, 2x times 1 over 2 times the square root of 16 minus x squared times the derivative of the inside by chain rule, negative 2x. To that we are going to add the second, which is 16 minus x squared times the derivative of the first. Before we go any further, I need to find a feasible domain for our x value, our x variable. And if you look back at the semicircle drawn, the smallest the x value can be is 0. And that is what happens if this corner and this corner of the rectangle meet directly in the middle. The longest this x value can be is 4, and that is if this corner and this corner of the rectangle start getting closer and closer and closer to the flat line, our diameter down here. So the feasible domain will be from 0 to 4. Now that we have this information, we can set this derivative equal to 0 and solve for x. Before I do any solving, I want to do some simplifying within each term if I can. And I can see over here that this 2 and this 2 will reduce away, and that I can multiply this x times this x over here to get a new term of negative 2x squared over the square root of 16 minus x squared plus 2 times the square root of 16 minus x squared equals 0. And to make things even better, I can multiply this first term by 1/2. I can multiply the second term by 1/2. I can multiply this right side by 1/2 as well. And what that does is it gets rid of these 2's, and 0 times 1/2 is still 0. Trying to make this as simple as I can for when I actually start solving this for 0, or for x. So this is negative x squared over the square root of 16 minus x squared. Now, to start solving for x, I need to multiply all terms by the square root of 16 minus x squared. 16 minus x squared, square root of that. And when you do that on the right side of this equation, you still end up with 0. What this does on the left side is that this will get rid of the denominator. When you multiply a square root times itself, the square root and the resulting square will cancel. And this leaves you with a negative x squared plus 16 minus x squared, which tells you that you have negative 2x squared plus 16 equals 0. And when you finally solve for x, you will see that x equals plus or minus 2 square root of 2. However, this negative version of our answer doesn't work because it's not in the feasible domain that we found earlier. From the previous slide, we know that we have a semicircle with an inscribed rectangle, and we figured out that the x value has to be positive 2 square root of 2. That's this distance and this distance. Also in the previous slide, we know that this value of the side of our rectangle was the square root of 16 minus x squared. Well, we knew that x is 2 square root of 2. And in fact, when you square that, you get that x squared is 8. So I'm going to substitute this 8 in for the entirety of the x squared and get that the length is square root of 16 minus 8, which is the square root of 8, which is 2 square root of 2. So we know that the height of our rectangle is 2 square root of 2. And back on the semicircle above, the length of the rectangle is those two square roots of 2 added together, which gives a 4 square root of 2. The original exercise is asking, what is the area of the largest rectangle? So we just need to multiply these two values together to find the area. So 4 square root of 2 times 2 square root of 2 is the same thing if you multiply these two numbers in front. 8 times the square root of 2 times the square root of 2 is 2. You will get 16 units square.